Okay, some more final points. Now we take a look at this reaction over here. This is the whole list of reaction that is possible for a nucleophile to react with an alkyl halide. Not all are in the syllabus. You just have to focus on those that are in your notes. Okay, so I'm going to go through two reactions over here. Okay, the nucleophilic substitution reaction with ammonia first. Now, NH3 ammonia has a very similar structure to water. They are very similar. The part of the molecule on ammonia that makes it nucleophilic is the lone pair of electrons over here. Have you ever wondered why water it is a bad nucleophile or it is a poor nucleophile compared to nitrogen? The reason is oxygen is a more electronegative atom than nitrogen. Therefore, the lone pairs of electron will be very tightly attracted to oxygen. Now, if the pairs of electrons are very tightly bonded to oxygen, this means that the size of the electron cloud is going to be very small, and therefore it means that in terms of overlapping with the orbital of the delta positive carbon in the alkyl halide is going to be very, very poor. Therefore, it cannot attack the delta positive carbon effectively through the formation of a bond by orbital overlapping. Okay, so water is a bad nucleophile. Nitrogen, although it is very electronegative, but it is less electronegative compared to oxygen. Therefore, the lone pair of electrons is still pretty much available for bonding or nucleophilic attack to the delta positive carbon. Is performed in a silk tube because ammonia is a gas at room temperature. Therefore, we need to keep in all the reactant, which is the ammonia, in a silk tube so that it doesn't escape. For the Cn minus reaction with Rx, the question we want to answer is this. Okay, why must it be ethanolic? Okay, why must the reaction be ethanolic? The reaction needs to be ethanolic because we need to dissolve both the Rx and we need to dissolve the Cn minus ion. Now, the Rx is not very soluble in water. The Cn minus is very soluble in water. And the converse is true for organic solvents. Rx is very soluble in organic solvents, but Cn minus is not soluble in organic solvent. Therefore, we need to choose an intermediate solvent that contains both the OH that is characteristic of water and the alkyl chain that is characteristic of organic solvent, so that both reactants can dissolve in a common solvent and that they can react. To state my point more clearly about the difference in reactivity between ammonia and water, let me give you one more example. So just now we talked about electronegativity and how it affects the size of the electron cloud that is eventually responsible for the nucleophilic attack. Over here, we can see a similar trend. Okay, now if F minus and I minus were to both act as nucleophile, which one would be a better and more effective nucleophile? I hope that you have learned what I said just now. Over here, I have a sp3 back loop for the carbon, which allows for the nucleophile to overlap, the orbitals of the nucleophile to overlap. F minus versus I minus. F is a very electronegative atom, so therefore the electron cloud for F minus is going to be very small. It has a very small electron cloud, or we call it in this case a small valence shell. So since the electron cloud is small, the effectiveness of overlapping with the sp3 orbital of the back loop of the carbon is going to be very minimal. There is going to be very little bonding, and the transition state is not likely to be formed, and therefore the reaction is not so likely to take place. Now if you have a bigger ion like I minus, the electron cloud is very big. Therefore, when it starts to overlap with the delta positive carbon over here, it can overlap from a further distance. It can also overlap very effectively. So, I minus is a better nucleophile compared to F minus. Okay, that is for the structure of the nucleophile. Now we look at the structure of the alkyl halide and determine whether a reaction can occur or not. So in general, if I have a CH3X, okay, remember I say you always look at the carbon from a tetrahedral point of view. I have 3 H's and I have an X. We are always looking at the space between the 4 atoms over here. The more space we have between these 4 atoms, the easier the access for the nucleophile is for the carbon. And that means that the rate of reaction will be faster. Now H is a very small atom, and of course you will leave a lot of space between the 4 atoms in the alkyl halide. Comparatively, if you have a tertiary alkyl halide, you will have very big groups that is blocking. For example, I'll just use R to represent the alkyl group. carbon itself is already bigger than hydrogen. Now imagine you have a very long tail of alkyl chain. The size of the carbon atom combined with the length of the alkyl chain is going to severely limit the space for access over here. So therefore, the nucleophile cannot overlap effectively. The orbital of the nucleophile cannot overlap effectively with the orbital of the delta positive carbon. Therefore, the reaction is going to be very, very slow. In fact, I can tell you, tertiary alkyl halides do not react via the SN2 mechanism because it is just impossible for the nucleophile to reach the delta positive carbon. Okay, now even more pictorial view. Okay, over here I have increasing degree of alkyl substitution on the carbon bearing the halogen. Over here I have a primary alkyl halide. Over here I have a secondary, and over here I have a tertiary. Can you see that the crowding of the carbon is black in color. The nucleophile is trying to reach the black carbon. The OH minus is the nucleophile here. So the OH minus is trying to reach the black carbon. But if you have more and more alkyl group attached to that carbon, that black carbon will eventually get all the way blocked up. Can you see? Therefore, there will be no access to the nucleophile, and the SN2 reaction cannot happen. Okay, so in this case, I have 3 different groups attached to the carbon, and I want to illustrate to you the inversion product of an SN2 reaction. Take note, SN2 reaction will only result in one kind of product. Okay, just one product. Okay, and that is because the SN2 reaction, the nucleophile direction of attack is only in one direction. So if it's just one direction, I can only form one kind of substitution product. Now later I will show you how to see the product for a SN1 mechanism. Okay, now in this case you can ignore the S and R here. It's not in the A-level syllabus. Okay, but just know that there is an inversion of the configuration from the reactant to the product here. Okay, there is an inversion. It's an inversion. Okay, so this is another view of the mechanism in a very pictorial manner. You can see the OH minus doing an attack using the lone pair of electron. Entering into the empty sp3 orbital of carbon. after that they form a bond over here in the transition state. This bond is about to be formed, and this bond is about to be broken. And in the end, you have an inversion of the product, okay, the organic product versus the original organic reactant.